Hi there. In this video, we're going to take a look at the integration technique of using trigonometric substitutions. If we consider the integral of the square root of 1 minus x squared dx for a moment, we realize that none of our usual integration techniques are suitable to find the antiderivative of root 1 minus x squared. Not even a regular substitution. Try as we might, it does not work. We can now consider a trigonometric substitution where instead of letting u equal 1 minus x squared, as I would in a regular substitution, I will let x equal to one of my trigonometric functions. In this case, I'm going to choose let x equal sine theta. I based my choice on two things. Firstly, we know that 1 minus sine squared theta is equal to cosine squared theta. So 1 minus x squared will become 1 minus sine squared theta, which equals cosine squared theta. And secondly, the restrictions on x is that x must be between -1 and 1, and we know that sine theta has a range between -1 and 1. Therefore, x equals sine theta seems to be a suitable choice for substitution. One problem with trigonometric functions is that they are not one-on-one, but we can fix this problem by restricting theta to a suitable domain. In this example, I can choose to restrict theta to the interval between minus pi over 2 and pi over 2, as on this interval, sine theta is a one-on-one function and it ranged from -1 to 1. Okay, so back to my substitution. If x is equal to sine theta, then dx is equal to cosine theta, and that would imply that dx equals cosine theta d theta. And now we are finally ready for our substitution. So x can be substituted by sine theta and dx by cosine theta d theta. As 1 minus sine squared theta is equal to cosine squared theta, my function will simplify to the integral of the square root of cosine squared theta times cosine theta d theta. Now we need to remember that the square root of x squared is equal to the absolute value of x. So the square root of cosine squared theta is equal to the absolute value of cosine theta. However, remember that we restricted theta to the interval minus pi over 2 to pi over 2, and we know that on this interval, cosine theta is never negative, and therefore on this interval, the absolute value of cos theta is going to become just cos theta, and my integral will simplify to the integral of cosine squared theta d theta. To integrate a cosine squared theta, I need to apply the power reducing formula, half 1 plus cosine 2 theta. And now finally we're ready to integrate. So half is a constant, 1 integrates to theta, and cos 2 theta integrates to half sine 2 theta plus a constant. Although we have now integrated the function, our answer is in terms of theta, but we need to write the answer as a function of x. We have the relationship that sine theta is equal to x, and therefore theta is equal to arc sine x. But we don't want to write sine 2 theta as the sine of 2 times arc sine x. So let us first use the double angle formula for sine to write that sine 2 theta is equal to 2 sine theta cosine theta and simplify. Now we know that theta is equal to arc sine x, and we know that sine theta is equal to x, but we do not have an expression in terms of x for cosine theta yet. For this purpose, we will draw a right-angled triangle with reference angle theta and look again at the relationship of sine theta equals x, which can be written as x over 1, which is therefore equal to the opposite of the over the hypotenuse, as we know the relationship of sine theta to be. So in my triangle, I can fill in that my hypotenuse is 1 and my opposite side is x. Using Pythagoras, I can determine that the adjacent side will be the square root of 1 minus x squared. And as cosine theta is equal to the adjacent over the hypotenuse, this will now give me the square root of 1 minus x squared over 1. And I can complete my answer to be a half arcsine x plus x times the square root of 1 minus x squared plus a constant. So in general, how do I know which trigonometric function to use in which situation? We saw in the first example that in the case of a square root 1 minus x squared, we can use a sign substitution based on my squared identity, but we also had to look at the domain of the function we wanted to integrate. We chose to restrict theta to the closed interval minus pi over 2, based on the fact that sine theta is a one-on-one function on this interval, and the fact that cosine theta, which is the other function involved in the squared identity, is non-negative on this interval. Let us now consider the square root of 1 plus x squared. Now, x equal to sine theta will not be a suitable substitution, as 1 plus sine squared theta does not occur in any of our squared identities. And also, in this case, the restrictions on x are that x can be from minus infinity to infinity, and that is not the range of a sine function. So, which trig function will we use in this case? Well, we know that the tan function has a range from minus infinity to infinity, and we know that 1 plus tan squared theta is equal to sec squared theta, which implies that x equal tan theta is a suitable substitution in this situation. Now we will restrict theta to the open interval minus pi over 2 to pi over 2, because on this interval, the tan function is 1-on-1 and range from minus infinity to infinity, and also the sec function, which is the other function in this squared identity, is positive on this interval. Let's now consider the square root of x squared minus 1. Be very careful. X equals sine theta is not a suitable substitution in this case, as sine squared theta minus 1 is negative cos squared theta, and we do not want a negative inside a square root. Besides, if we look at the restriction on x, we realize that x squared minus 1 must be greater or equal to 0, which implies that x must range from minus infinity to minus 1, and then from 1 to infinity again. Now, the trig function that has this range is the trig function sec theta. And we also know that the squared identity sec squared theta minus 1 is equal to tan squared theta. So x equals sec theta is a suitable substitution in this case. The restriction on theta is a little bit more tricky in this situation. We choose to restrict theta to the interval 0 to pi over 2, which is the first quadrant, and pi to 3 pi over 2, which is the third quadrant. Now, why do we choose the first and the third quadrant? Because we need our sec theta to range from 1 to infinity, but also from minus infinity to minus 1. And at the same time, we want tan theta to be positive on the intervals that we work on, and therefore the first and the third quadrant is the suitable restrictions on theta. So in general, if I have the square root of the form a squared minus x squared, for example, square root 4 minus x squared, I need to change the amplitude of my substitution. So in this case, we will let x equal a sine theta. Theta restricted to the closed interval minus pi over 2 to pi over 2. And we will still use the squared identity that 1 minus sine squared theta equals cosine squared theta. If we take a look at square root a squared plus x squared, we need to substitute x with a tan theta on the open interval minus pi over 2 to pi over 2 and use the squared identity 1 plus tan squared theta equals sec squared theta. In the case of square root x squared minus a squared, we will let x equal a sec theta on the first and the third quadrant and use the squared identity sec squared theta minus 1 is equal to tan squared theta.